I don't know.
Well, some of them are not in the visible spectrum.
Some are not in the visible spectrum, Anyway, so this is the cluster Westerland 2. The star cluster is sort of in the middle of the screen there, and it's illuminating a gaseous cloud around it.
So for the most part, if you were flying around in space, and let's say you had a ship that was faster than light or whatever, or warp, whatever, what you would see pretty much would be what we see in the night sky, like all the time. Like that's what it would look like. You would never get.
Pretty much, yeah.
I mean, if you went close to a nebula, you would see that would dominate your view. Yeah.
But the kind of
a lot of the time,
super dramatic, overarching, Horsehead Nebula, crab.
You would have to be in the right place.
Yeah,
right. You have to be in the right place and the right distance. And then there's a lot of things that, there's a lot of false color in there.
But for the most part, it would look just like stars on a black.
I think so.
Yeah.
Well, what about a planetary nebula to the naked eye if you were close? I mean, that would probably look really cool, wouldn't it?
Could you get the Star Wars
on the nebula, right?
Yeah.
Could you get the Luke and Leia shot from?
Yeah. I mean, if you're at the right distance, yes.
But
it wouldn't be turning.
They're looking at a galaxy. It wouldn't be spinning.
Yeah.
All right.
That would be truly beautiful.
Next picture.
Yes.
The happy face. Do you guys? It looks like a happy face. A smile. Do you guys know what that is?
Of course.
It's
space.
It's
a gravitational.
It's our universe.
It's the comedian.
So those are galaxies.
Why is
that
that
we're
happening?
seeing. Those are not stars. Those are galaxies.
So those lines that make the outside of the face.
That's
gravitational lens. It's smearing the light.
So that doesn't exist. That's the one thing that doesn't exist. That's just an artifact of gravitational lens.
What are the two eyes, though?
Those are galaxy clusters. Okay. Those are galaxies. They're globular galaxies.
Is it a singular one that we're seeing twice, or there's actually two?
I think those are two that just happen to be so close to each other in terms of how they appear that it comes across as eyes.
That's
right.
Great.
Because that does happen sometimes, right? Where you have one and then you get some anomaly and it appears on both sides.
Yeah. Right. Yep.
I think with most known gravitational lensing effects, you get more than two copies.
Yeah.
Yeah.
Okay.
So I think it would be. I don't think that's completely impossible, but it would be unusual.
Right.
You can sort of see there's like in the lensing there's some coloring.
But does this mean that the universe is a pedophile? Because that's creepy.
It is. It's
a galactic smiley face.
It's that smiley face that used to be on that ice cream cone.
That's a creepy.
Thing.
That's creepy.
That? But the thing is,
some space is not creepy.
What are the odds? What are the odds of having two perfectly placed globular galaxies and a nose, a little button?
But from our perspective, if you went 20 light years in that direction,
seeing basically the two-dimensional projection onto the lens of the telescope.
Right.
That's
but the thing is, there's so many places to point that telescope at the universe. It would be amazing if we never found anything like that. But
there should be more of these, frankly.
Yeah, the only way that would be better if it was a full circle instead of two kind of semicircles.
Your brain,
of course, yes.
You fill in the blanks.
It's wonderful. I love that.
Hey, so one of our Phil Plate said, dudes, not lenses on Hubble, mirrors. Sheesh, do I have to come on at 8 Eastern Standard Time and lecture y'all? Yes, he's right. It was mirrors.
Yeah, you come here. You show your face here on Skype. I dare you.
Thanks, Phil. We should have noticed that.
At least Bob should have picked that.
Yeah.
Yes.
That is now that's something I would like to see outside of my window.
That is one of the most beautiful galaxies. That is the Whirlpool Galaxy that we happen to be seeing face on.
Awesome.
That's a little satellite galaxy next to it. So there's two galaxies there, right? Just an absolutely gorgeous galaxy. I mean, I don't know what else to say about it. One of my favorite.
Dramatic. I've never seen them look quite like that, though. What kind of filters are they using? Is that partly infrared or what?
And then the distances between every point of light that we see here.
Yeah.
Like between those points of light, it's just pure black nothingness for millions, if not billions of miles.
I know.
Trillions of miles.
I know, George. If
we look at it. I mean, what is this? 100,000 light years wide or 200,000 light years wide?
Say 100.
It is.
Yeah.
Right. So between every single point of light that we see,
it's probably millions of light years away.
Yeah, and it's millions. But just if you were inside there, all those points of light would be.
Yeah.
It's like you wouldn't feel this like
it would be like
Whirlpool.
It's like us on Earth.
It's like us on Earth.
You would just be seeing a little patch of stars around you. Yeah.
And this is probably hundreds of millions of years old as well. This is an old shot of it. Who knows what it looks like now?
All right, this is the Eagle Nebula.
Yes.
Nebula are definitely beautiful.
Why do they call it the Eagle?
Well, Bob.
I don't know why.
I thought you had it right there, Ed.
Because it's 100 par. No, 200 par.
200 par.
Very good, George.
Yeah. It's 9.5 light years tall. Yeah.
It's
huge. These are huge
it's just huge. You
structures.
can't.
Yeah.
I mean,
Cut the head off there. Maybe about
These are all
half a
Hubble.
light year.
These are all Hubble.
That's a really
Some of them are composite, like the Hubble with another telescope.
Composite.
Composite, whatever. This is the Centaurus A galaxy, which has a lot of dust in it. So that's what we're seeing. There's a lot. It's very bright, but
Dirty
there's a lot of dust, which makes the dark areas.
That's really awesome. Go ahead.
Okay. This is the Helix Nebula.
That's definitely God's eye.
yeah.
Isn't that the eye they used in Cosmos?
It
sort of
looks
looks
similar.
like it.
to
That's
looks
very
like
similar.
that.
It's not inspired by it. So this is a composite image. This is,
But it does have an eye. It does have like the look of an eye.
Totally.
You know, it has like the lines and everything. That's really
so
amazing.
it looks like you're looking like at a donut, or you might think you're looking through a sphere, but actually that's two perpendicular discs of
Perpendicular.
gas. Yeah.
Perpendicular.
Yeah,
How do you get that?
looking at two different discs, kind of making that.
Really?
The light blue ring is one. That's what you're saying.
So you can kind of see like there's one yellow ring, and then there's
Yes.
another ring facing, and it's actually facing another direction.
Is
Just
it?
from our perspective, it gives this illusion.
Oh, I see. Yeah.
So it's like
Oh, yeah,
Cool.
okay. I kind
See
of you have
that?
to
Yeah.
do that 3D
Is that
thing
dark
in your
blue
head
thing
to
that looks like the
turn it.
Batman symbol a little bit?
Yeah.
Yeah.
Yeah, it does. You're right.
Yeah, there you go.
Wow,
How interesting.
it's a long
All
way
right.
for the Batman.
Whoa, this
Whoa,
is
that
one of
is so
my
cool.
favorites.
Now that's the Death Star exploding.
That's not sombrero.
Sombrero, very
yeah.
good. That's Sombrero
See.
Galaxy.
Cinco de Mayo soon.
That's one of my favorite. That's a
Well, it's just like
dramatic.
it's so bright in the middle, and then you have the dark
Yeah.
fringe around the outside, and we're watching it at this sort of perfect angle.
Yeah.
It's just
Isn't that unusual
gorgeous.
though to have that much dust on the extremities of the galaxy?
I don't know if it's unusual. It's the way this galaxy is.
It's the
There's
way
so
it's
much
illuminated,
variability.
Bob, because the light
Phil,
behind
Phil?
it.
There's so
Tweet the
much
answer to that.
variability in galaxies, as we'll see.
It's not dust. Those are Thetan souls that have not gone to the planet yet.
Oh,
It's a lot of people make that mistake.
Yeah.
Hubbard.
That's
got
common.
us
All right,
again.
that feels bad. What else you got?
Okay. All right. What moon is that? Peeking around Jupiter.
Well, that's
Each a Jovian one.
Ion.
Ganymede.
Ganymede.
Boom!
Ganymede.
Nice.
Very
Wow.
nice.
Need.
Very nice. So yeah, so the Hubble can take pictures of our planets as well.
That's awesome.
Oh,
Ooh.
That's obviously an explosion.
It's
Yeah,
the
that's-
Bill Nye bow
that was
tie
like a
nebula.
supernova.
what does it look like?
Bill Nye bow tie nebula.
Rorschach
That's
test.
awesome.
This is
you.
a Rorschach
Rorschach,
test.
yeah.
What is that?
I see.
What's the name of that nebula?
Butterfly?
Butterfly.
I would think
Oh,
butterfly.
Butterfly Nebula.
Oh, I thought it was 2
cool.
points for
I
that.
didn't know that.
He's in the lead.
So the sun that was at the middle of this was a 5 solar mass sun
That's
that,
big.
that exploded. That is a planetary nebula, a completely misnamed planetary nebula.
All right, so the sun exploded, and now more planets are going to be created from that.
No, it wasn't. Well, if it's a planetary nebula, it was not a
Jay,
supernova.
Come on.
Well, a nova. What makes a planetary nebula?
Well,
I know
a-
all
like a
things near
sunlight
and
star
far.
that would shed its outer layers.
Yeah, yeah.
Right.
This
So
is
that,
cooking.
Isn't that a nova though when it does that?
no, our sun's not going to nova.
It won't turn into
It
another
just
star.
sheds its outer.
It
layer,
sheds its
mass,
outer.
right?
but it doesn't explode.
It's not big
Right.
But they were called planetary nebula initially because they thought they were like a planetary disk forming, like a sun, but it's not. But the name stuck, even though it was based upon a complete
Yeah.
misunderstanding of what they are.
I've gotten over it.
Like
Like the whole Pluto thing.
jazz.
Finally over that.
That's neither. Yeah.
Right? Yeah. We had that.
Total misnomer. Total misnomer. Yeah.
There's so many misnomers that stick in science
yeah,
because it's
yeah.
just precedents, military.
I keep looking for Phil's corrections on
Wow,
Twitter.
All right, this is star cluster Pismis 24.
Pismis?
I guess
That
This
is
must be my
awesome.
lucky day.
That is gorgeous.
You really need
that
it.
literally is the backdrop of a future movie
I was
poster.
gonna say you need like a battle cap.
Yeah,
on there
that's
or
it.
something, or
Yeah.
like He-Man with his sword straight.
What's
up.
the blue, the blue, light blue light in the bottom there?
I think it's just a blue star.
Just a
Yeah.
yeah. Cool.
Why are there no green stars?
That's
gorgeous.
the Kmart Nebula.
Because nothing burns at that temperature.
It's more complicated than that.
Shut up.
Phil will tell us later. He's on the show.
Phil.
These are two
1, 2.
galaxies colliding.
Uh-huh.
This collectively they're called ARP-273, two interacting galaxies. So that's the other thing. Galaxies are very variable themselves in terms of how they look. But every time two galaxies merge gravitationally, you get this random gravitational splash, and there's all kinds of cool stuff
Well,
happening.
you could see the tidal distortions already on the bottom galaxy. pre-impact.
I've played with software that lets you like do this, like you can
Lets you collide galaxies.
Yeah, it's pretty cool.
Have you ever seen that Galaxy Zoo where you can help determine the spin?
Yeah, I
of a
did.
thing?
Oh no.
You
Pamela-
look at galaxies.
Pamela
and
Gay
you-
sort of arranged this thing. Yeah,
Cool.
so they give you raw data and it trains you how to determine the spin, and then you determine it, and it's kind of like what do you call it? When
Crowdsourcing.
Crowdsourcing.
Cool.
And then they do that. They've done it for moon.
By spin, you mean like
craters.
how the angular momentum, like how?
Like which? I guess they all go in
which
different directions.
direction
Yeah,
it's
which
going.
direction
I
it's
see.
going. Yeah, because there's certain indicators that tell you which direction it's going. They teach you, and then you sort of do it, and then it's a crowdsource. So then it's sort of agreed because there's just too much data to go through for all these researchers. So there's that, and then there's like a moon zoo where you can determine crater impacts, like how old they are.
And this is stuff people at home are actively. It's not like the SETI at home thing, which is just sort of running in the background. And you're
Yeah, no, you actually go
doing
and you determine and you say, oh, this is a clockwise, counterclockwise,
that's-
whatever.
Yeah,
the
they
terms
teach you
are,
how to do it. I think it's also
Cool.
where
It's great.
you're deciding, like, is it a cluster galaxy? Is it a barred spiral? Is it
Yeah.
a spiral? They teach you how to do that.
Yeah, they
too.
keep expanding on what you can do, and
so
they use it all. It's great.
This is star V838 in Monocerotis, which is the unicorn, the unicorn nebula. And I tried to understand what they were describing here. I think this is the star in the middle of it here, and this is another, I guess, planetary nebula. And these are light echoes. So these are not multiple stars; they're just visible echoes of the one star.
That can be only
It
one.
bounces off the different layers of the nebula, and so that's why they're displaced. But
I don't know.
That's pretty damn cool.
That looks like
sure?
that looks actually like a hornet's nest, kind of. You know, like that
Yeah.
that paper
Yeah,
and stuff.
right,
in
Jay,
there.
right.
Okay.
That's
Okay.
something.
What else we got?
Hornets paper, I like that.
Wow, that is.
Oh,
cool.
that's
That
This
is
is
so
has that
cool.
3 light
classic
years
sort
tall.
of Hubble.
Guys, let's have a moment of reverence and perspective here. 100 years ago, not only did people not know that this was there, but they never could see stuff like this. I mean, think about how fortunate we are that we're seeing images of
Yeah.
the far reaches of our known universe.
Was Hubble the first telescope in orbit?
I think so.
The first one.
Telescope.
Telescope.
Yeah, I think so.
Yes, it was.
No.
That is clear. This is clearly the Bearded Man Nebula.
Where there weren't smaller ones put up.
What do you think?
Yes, it's the Bearded Man Nebula.
What else? Any other guesses? What
oh.
the pareidolia is here?
Pareidolia.
I see a guy with a mustache and a
It's like the
beard.
United States.
This
sort
is
of
the
an outline.
Ghost Head Nebula.
Oh, of course,
come
it goes
on,
like
that could
that.
be
Yeah,
it.
it's good.
Yeah.
Like
Any
ghost
blobs?
I
Like,
guess
Yeah,
there's
right.
blobs in it.
Yeah, a sheet
Am I seeing
hanging
that
over
right?
the
the Ghost Head Nebula. Pretty cool.
Who gets to name these? Is it like the person?
Frankie Gismore.
I know him.
Does he just? Oh, wow, it's a good game.
Look at this.
Oh, that's NGC 4038, right?
Yep, that's right. And 4039, two interacting galaxies again. Okay, just
Great guess, Jack.
very cool.
Yeah, it's like you read it somewhere.
I'm cheating. Watch this. I'll do it again. That's isn't that the Mars close approach that happened on June 13, 2001?
No,
No,
you
just
gotta
well,
look at
Jay,
the order,
get
Jay.
Get milk before show is done.
This is not on my list. Why?
Ooh, pretty
Let's go to the next one.
Make
That
a
should be the.
Steve, isn't that the Mars approach from June 13, 2001?
That's Mars. Very good.
Okay,
Well
yeah.
done.
Now, what's that thing on the top?
That's
Impact
a polar
crater.
ice
No,
cap.
polar ice cap.
Sure.
Yeah, I'm pretty sure.
ice ice?
I think it's CO2 ice.
Yeah.
That's a beautiful.
Where's Mars
or
1
water
gonna,
ice, too.
We'll be talking about water on Mars later.
Point where Mars 1 is going to camp out.
Mars is a cool planet.
Oh, look at that.
Whoa, I have never seen that one
Damn,
before.
that's so cool.
Is that a ring
That is
galaxy?
amazing.
That is a flocculent spiral.
Hey,
Yeah.
this is a family friendly show here, Steve.
So now, is that center light is millions or so many stars you can't count them, right? That's not one star. That's a ton of stars together. Lots of solar systems and
Right.
all that.
Yes.
And now, is that all slowly going to just keep swirling in?
It's
and
a
get
spiral
tight?
galaxy. It's just that
It's
it's
a
lots of
spiral,
sharp, lots of short arms rather than well-formed spiral arms. You
Yeah.
know what I mean? So it's just
Yeah.
another kind of spiral galaxy called the flocculent spiral. But isn't that cool? Look at
That is
that.
damn cool. And
The level of detail is
the,
insane.
the angle of it is really
is.
cool. It really feels like you're on top of it.
Flocculent is like flocking, like in a like for, where you splatter paint. Is that?
Maybe. Is
that
that
where
what the
that's
word
from?
means?
Is that
I've
flocking?
never heard that term before.
Flocking.
Flocculent.
But you have to do that. with your
This
hands.
is another.
Like
when
like a
galaxies
pointillism
collide.
sort of thing.
Yeah.
I would call this one the wrench galaxy.
wrench. It's
So
near
the
two
Pac-Man.
galaxies interacting.
Pac-Man galaxy.
The
It's
one-
like
the
a
one-
bottle opener.
The other
Hawk.
one is off. I think
Baby
it's off
bird.
frame.
Right.
Baby
Yeah,
bird
it's
galaxy.
Very nice. That's the last one.
That's a
Okay,
very
that's
nice.
awesome.
It's a stasis.
Hubble.
That's
Thank
from,
you, Hubble.
Dark
Thank
crystal.
you, Hubble.
amazing.
Aren't those
Hubble rocks.
gorgeous?
Now talk about a project that overachieved, right?
That's one
Yeah.
of them.
Yeah.
Once they
Probably.
got that lens, that mirror thing figured out.
And now we got the James Webb going up soon. That's going to be
How is that
Amazing.
different from Hubble?
The mirror works.
it works right.
Is it bigger? Is it
bigger.
Is it
It's
more?
Thank you, Hubble.
Does
Now,
it have
Brian,
a,
you had something you were going to do, right?
Yeah, it's something I was
trick?
going to try.
A magic trick? I love magic tricks.
So I was thinking when I knew I was going to come and hang out with you guys for this, what fun thing could I do? And have you ever heard this thing when you write a book, right? For every equation you put in, you lose half your readers, right? It's something I think it's in maybe even the preface of Brief History of Time.
Yes, he was
Right,
told,
he
right?
told
Just
it, don't put in any
and he's
equations.
like, no, I've got to put
Yeah.
at least one. Of course, E equals MC squared.
Right. But I think that's kind of crap because the way theoretical physicists think about the world is through equations, right?
Okay.
So I thought it'd be fun to take what I consider essentially the most important equation in particle physics and try to explain it or give you some sense of what it means to a particle physicist.
Okay.
This might completely fail. It might be totally incomprehensible, but I figured if anyone can understand it, you guys.
Wait.
We'll try. We are going to try.
can.
So what are you doing?
So-
Yeah, start over again. What's happening?
Sorry.
Great. So the equation I'm going to explain.
I got them here.
you got it. Is
What
it-
do you want me to show?
Pull up the
Single one? This one?
No. The PDF one.
There's two. There's this one,
Not that one.
and then there's this
that one. Yes.
Oh,
okay.
boy.
So this.
Oh, this whole
This
trope.
is yeah.
What language
this whole
is that
thing.
written?
This thing. So first of all, credit where credit's due.
This is my PIN number, by
Hold
the way.
this.
This is my old email address from CompuServe back in 1991.
I pulled this off. I'm not sure if Sean Carroll made this or if he got it from somewhere else, but I pulled this
Sean.
off his blog. He for a while. I think he still does this. Every year at Thanksgiving, he was putting something that he was thankful for. And this, I think it was from 2006, he said he was thankful for the standard model of particle physics. So first of all, what is the standard model of particle physics? It is every particle we know that describes, the universe that we see, the matter in the universe.
Matter.
And its interactions.
yes.
That's right.
Yeah.
So to a theoretical physicist, right, you can't just say, here are the particles, here are their interactions. You need some kind of mathematical representation of that. So this is part of the equation that describes the standard model of particle physics. And
How small of a part are we talking?
So what this is this is basically what describes one generation of the standard model. So the way the standard model works is the quarks and leptons. Leptons are things like neutrinos and the electron. They come in 3 generations. So for the leptons, you have an electron and a corresponding neutrino. That's one generation. Then there's a muon, which is a particle like the electron, but much, much heavier and unstable, and its corresponding neutrino. And then there's a tau, which is much, much heavier than even the muon and has a corresponding neutrino.
tau's
So there's
really
a
heavy.
electron and its neutrino, muon and its neutrino, tau and its neutrino. This is only one of those things. And the same thing is true with quarks.
Brian, doesn't a tampon absorb other neutrinos?
Yes, that's correct, Jay.
Thank you.
Great joke.
What the?
With the quarks,
There's no Higgs. There's no
we're
Higgs.
here all day.
so
Okay.
I want to see the Higgs equation. It's not in here.
the other thing is the quarks come in generations too. There's up, down,
Yeah.
charm, strange, top, bottom. So this is also only the up and down
left, right.
quarks. So there's the whole left and right. Actually, if you look at these equations, you can see some on that number 2 there. Right, you see some L's and R's.
Yeah.
Right. That actually means left
right.
and right.
I know. Hey,
Because
that
because they're
That I
left
understand.
quarks and right quarks. And the thing that's amazing about left and right particles, and I'll get to explaining this in
So this is 5% of the universe what we're looking at right now.
this is a third of 5,
Third
right?
of-
Because this is
third.
only basically one generation
I
of
see.
the
There's
standard
2 other
model.
generations.
There's 2 other
I got
generations.
it. Gotcha.
What's the proportional difference between generations? You said it's much heavier. Like how much heavier is?
It depends on actually with the muons. It's
be hundreds of
embarrassing.
times,
I
right?
think the muon it's 2,000
2,000?
times the mass of the electron. Actually, I can't quite remember, but it's a 200 or 2,000.
Okay.
10 to the 2, 10 to the 3.
Yeah, my vote is 200.
Yeah,
Brian,
but
somebody sat down.
the quarks are different though.
Like this, I'm sure this evolved over time, but somebody actually started to think about this equation. They wanted to come up with this equation, right?
This
isn't one equation, right?
That's right. So basically,
not-
this is the sum total of our knowledge. You asked how long would it take for people to, get particle physics back. Basically, this is what we understand of particle physics.
So if this podcast survived
Yeah.
the zombie apocalypse, They would
we
be
would
most of the way there.
Yeah, we would still have this. But one thing that this doesn't have, which I'll get to maybe in just a second, is that this doesn't have the Higgs. So this is actually the equation after the Higgs has given mass to the fundamental particles.
Okay.
It's Higgsless.
It's Higgsless. Well, it is. So
Higgsful.
if you remember from a couple of weeks ago, we were talking this transition, right, from the theory with the electroweak force, where the electric force and the weak force are unified, to the theory that just has the electric force. And this happens as the universe cools down. We go from the electroweak unified era to the electric. That is when the Higgs, that is identically when the Higgs gives a mass. Yeah, spontaneous symmetry breaking is what it's called.
Sorry.
Yeah.
What's
going on?
In very simple terms, what does this equation tell us?
This tells us all the fundamental particles, their masses, and how they interact.
All right,
with the
perfect.
forces they interact with.
That's
I get
huge.
that.
That's a lot.
Yeah,
That's huge.
it's huge.
And how many man years did it take to come up with this?
Man years.
This was, I mean, it depends how far back you count,
Right.
right? You could count back to Democritus, you could count back to Newton, you could count back, to any, depends. If you want to go back to the beginning of
2,000 years.
Yeah, pretty much. I think that's
1,000
probably
years
fair.
of people thinking like crazy to come up with this stuff.
Well, I mean, the standard model in this form, even its earliest, most primitive form, isn't that old. I mean, right? People
This
were
was
talking about the standard model, what, decades ago?
Yeah, so
100 years
basically, in this form, I would say this was known in the late 60s.
Okay.
The part of it was known in the late 60s, and then more of it came into focus kind of as the 70s went on. Roughly speaking, certainly by the end of the 70s, this was widely known and appreciated, even though we didn't quite know the masses of all the quarks.
Right.
For example, I think the top was which is the heaviest quark.
Yeah.
That was found in 93 or 94. I think that's when its mass was locked down, which is only 20 years ago, right? But the 60s, 70s was when this all sort of fell into place. So people think of the 70s kind of as the golden age of particle physics, when we really, figured out that what we were talking about.
Okay.
Because of all the cocaine, right?
Oh yeah, totally, dude.
Now,
It was
Brian,
just crazy.
if I just swapped one of those F's for the letter Z,
The universe would
what would
collapse.
happen?
That you can't do that.
You can't do it.
So should we try to?
Let's take a look at the
go through this?
equation.
Okay, so equation 1 basically doesn't really mean anything here. It just says, hey, the full equation is the sum of everything else below this.
The LSM equals L
Yeah.
Dirac.
Yeah, what's the L symbol?
The L stands for Lagrangian, which is it basically means this is the fundamental equation that describes all the interactions and all the particles.
Okay.
That's
So
where that
SM is the standard model.
SM is the standard model. Yeah.
Oh, is that what
At
that
least
means?
in this context.
Yeah,
Yes,
that's
okay.
right.
I was thinking, 50 Shades or something.
Then it's something totally.
50 Shades of Physics. You should write a book called 50 Shades of Physics.
Ooh, I like it.
That's a bestseller.
It's trademarked.
That's what
Thank
that
you.
is.
All right, I got
I'm literally looking at
just
the
trademarked.
first three, the LSM, and I don't get it.
What that means is here's the set of interactions and here's the set of particles and their interactions.
All right, so
Basically,
say all particles and their interactions equals.
this thing.
standard model.
Yeah. So
Lagrangian was a person? Was it a scientist?
Lagrange was a very famous French scientist from I think it's the 18th century.
Do Lagrangian
Okay.
points come from him?
Yeah,
Yes,
exactly.
it must be, right?
So the standard model equals a bunch of these other equations.
Yeah. Just to say this real fast, there's you can reformulate all of Newton's laws in terms of a Lagrangian, which is sort of it's a higher level approach to summarizing kind of all of mechanics. So there are two famous approaches to classical mechanics, which are complementary, one due to Lagrange, one due to Hamilton. And you can basically sum up in this object, the Lagrangian, kind of the properties of almost any system. So it really is sort of like an equation that I hand you, I write it down, and then you get everything for free, and then you just work.
Right. So if you gave
It's
this to a super intelligent robot, say like maybe Ultron or maybe somebody more benign, they could extrapolate pretty much most of the universe, except dark matter, dark energy, but the visible universe from this equation.
Pretty
a lot
much.
Of it.
Although there is an interesting thing to say, they could extrapolate the microscopic universe. One thing that is famously a reason that condensed matter people, like solid state physicists, hate particle physicists for is that you wouldn't get, for example, emergent phenomenon like superconductivity, any kind of very complex behavior from a microscopic description. Sometimes knowing the microscopic laws, once you get a large number of particles, they have this sort of aggregate behavior that this really doesn't reveal in any meaningful sense. So you could say, I mean, in a very real sense, this is not super useful for our macroscopic lives. It's only useful at the very microscopic phenomena, microscopic scales that you'd see at like the LHC or.
Well, could you take this and then run simulations and then extrapolate? And wouldn't you, if you had a properly sophisticated simulation, wouldn't emergent behavior possibly come out of it?
In principle, yeah.
Right.
If you had a really super computer, then in principle you could see all this.
But this doesn't imply like Newtonian models, or it does. Large scale stuff. You have to.
So this does not imply something like, so this wouldn't imply like Newtonian gravity, for example. This does, famously the standard model has doesn't speak to gravity at all, and that's a big, basically the problem is that the
we
language.
don't know a lot about it. We just.
It's not even that, it's actually that the language you use to describe this Lagrangian sort of approach, when you start doing calculations with it. Now I could write something down like this for gravity, but if you start doing calculations with it, you get infinities. And very famously. Well, and famously, in here in the standard in this Lagrangian, you get infinities that you can fix, which is called renormalization. Yeah. In gravity, you get infinities you can't fix, and there's a problem.
It's called magic.
Yeah. So this is why people go on and on and on about wanting to find a theory of quantum gravity, because basically what this Lagrangian specifies is a quantum approach to the standard model. So then you can't combine it with the gravity language.
Right. So then this doesn't really speak to general or special relativity.
This is going to be consistent with special relativity.
Special,
but not
general
relativity.
Oh my God.
Special relativity means that things can move fast. And of course, so just to say this, right? If this were wrong for special relativity, we wouldn't understand the LHC. Right. Because everything at the LHC is moving so quickly. Right?
Now, Brian, don't take this the wrong way, but you're doing such a fabulous job. I'm going to use this opportunity to take my first bio break.
Yeah,
so
sure.
You got this.
Okay,
you're good.
great.
I got it, Steve. Hang on.
Right, cool.
So wait. So then, are you saying that
water actually?
Yeah, I'll get you.
Thanks.
So Brian, are you saying that? All right, then the standard model kind of meshes with standard or special relativity and quantum mechanics, but not general relativity. Is that the main?
That's right. So the mathematical framework, the language you use to describe particle physics, is something called quantum field theory, which is essentially don't even worry about that, but it basically means quantum mechanics plus special relativity. So it is relativistic quantum mechanics. General relativity is the theory of gravity, right, which is a whole other ball of wax.
And that's what one of the holy grails of physics: quantum physics and general relativity. Those are the two bad boys we want to get together that we just haven't done yet.
Well, we have, because, for example, string theory is a theory of quantum. Now, I don't know if it's right, but it is a theory that successfully combines. Unifies quantum mechanics and gravity. And there's actually a very nice heuristic way of seeing why string theory does that for you, whereas this doesn't.
Brian, you're doing such a good job. Don't take this the wrong way.
You're going to leave too.
But I'm going to take my first methamphetamine.
Okay, great. It would be great if slowly, one by one, all of you just laughed.
This is actually a huge punked episode.
Brian, I'll hang you down.
8 hours.
So here's the reason that string theory fixes this problem, whereas this Lagrangian doesn't. Or standard quantum field theory doesn't. The problem, all these infinities basically come from when you start calculating things like scattering amplitudes, the probability that two particles are going to scatter off each other into two other particles. Famously, basically anything that can happen might happen, so you have to sum over all possible possibilities. Right? That's kind of what quantum mechanics does. And all the infinities basically come from when things get very, very close together. Yeah. All right, so when things are super, super close together. And that, if you're careful about it and you do the gravity calculation, you see their infinities coming from that sort of thing. But what string theory tells you is, at some point, which is the size of a string, don't use this point particle crap, right? Really, what you should use is whatever string theory tells you to do. So basically, it takes away these infinities from things getting really close together by saying, look, once things get close enough, use this totally other formalism, which when you do the calculation in string theory gives you a finite answer. So the reason string theory works but point particles don't is because string theory says once you get close enough, you shouldn't be thinking about point particles.
It's because it's no longer a point particle. It's some sort of extended string object.
That's exactly right. And when you do the string calculation, then you get a finite answer.
It works.
It works, and that's the amazing thing about string theory. Yeah,
But
and I think that's a very intuitive reason.
Yeah.
Right? Basically, this language just breaks down at some point, and there's this other thing. It's kind of like, it's actually a perfect analog for, we know Newtonian mechanics works when things are pretty slow, right? But when things get faster and faster and faster, we say, look, the Newtonian mechanics gives sort of crazy answers, right? You need relativity, which is consistent with Newtonian mechanics in some limit.
Right, faster and faster, or heavier, more and more gravity. That's where they break down in those
Right, if you were doing,
regimes.
for example, that's right. So if you're doing general relativity, exactly. But the way string theory works, for example, is it says, look, string theory is consistent, and in some limit, it gives you all this quantum field theory and gravity stuff back again.
Right.
So it's in some sense, a larger theory that subsumes the other theory, which you can then recover by taking an appropriate limit.
Right, but it's still not a fully fleshed out quantum gravity. Right, we're still far from being
No,
like
it is a quantum theory of gravity. It works for that. Is it the theory that describes the universe? That it was really unclear and probably isn't true. But I don't think you can take issue with it is a quantum mechanical theory that describes gravity. That's just a true statement.
Okay, you're right. Okay, then. So is the problem then that it's just really hard to test? That it's maybe not impossible, but it's hard to test to say, yes, this makes predictions that we can actually test and verify. I mean, what's the major stumbling block?
That's the big one with string theory, is
Yeah.
that it's to see these effects that would come from strings, you need to build not just an accelerator that's like a little bit higher than the LHC in terms of energy. You need to do something, if you're going to test it through accelerators, something that is so energetic, that makes things go so quickly that it's basically never going to happen in human history.
Yeah. Or one thing we've been looking forward to being able to determine from quantum gravity is to predict what's happening inside a singularity, right? I mean, that would be by definition an event or process that requires quantum gravity to really get some insight.
What I would say is what we would love to do is to remove the singularity, right? In kind of classical general relativity, we think of singularities as this thing exists at some space-time point, and really the fabric of space-time breaks down there. In a really nice theory, what you'd like to do is say, no, we kind of resolve that singularity. We know what's going on there, and it's not a breakdown of our laws. It's this other set of laws that we understand better. And one thing we can do, one cool thing that string theory does, for example, is you can create black hole-like things out of strings and brains. And it does offer a bit of insight into that.
Right.
Yeah.
So you get this.
Oh yeah. So that's right.
I have a question now.
Sure.
So you're hanging out with a bunch of, and this is not a joke. This will be interesting if the answer is yes. You're hanging out with a bunch of other people that are as smart as you about this topic. Do you actually joke about this? Like, do these come up in jokes? Like, you play off it sometimes. You reference something that's so heady and so like in your sweet spot that.
Sure, like any group of people that share a knowledge base, right? It's not even smart. It's just knowing the language. It's knowing actually for jokes. It's like knowing the words more than anything. And so,
but would you be like, so I was talking about L mass equals minus V. It's actually minus Q.
That whole one.
I probably
Lagrange.
I would be lying if I said I hadn't seen things pretty much exactly like that.
Exactly. Okay.
Yeah,
all right.
pretty much exactly like that.
Explain this first line. What are our terms here?
Okay.
What are terms?
Yeah. So the equation 1, right, just says sum all the other equations. That's the the master equation is the sum of everything below it. That's all it says.
Understood.
There we go. So what equation 2
But
is...
wait. Can you tell what the terms that we have in that first equation?
Yes, actually, my eyesight is so bad. Let's see. So it's L Dirac. That's let's go through it one by one because I think that'll be the easiest way to explain it. So L Dirac.
Yep.
All those are those are the you see there's a.
It's number 2.
Oh, I see. They're spread out that way. Gotcha.
Yeah. So that's right. Equation 2.
Mass
Basically, those are
3
all the particles. And that's their kinetic energies. Those are essentially, I mean, this is a little bit imprecise, but basically that's the thing that says those particles have dynamics, they move, they have kinetic energy.
And Dirac is a person as well.
Yeah, so what Dirac did is he basically found the relativistic theory of a fermion, of the electron.
Oh, yeah.
Right? So the question is, what is the equation? So the Schrodinger equation, for example, is a quantum mechanical equation that gives you the behavior of a non-relativistic system. And a big question for a long time was if you have something that has spin, something that has internal angular momentum, like an electron, what is the equation that governs the electron? The electron, or indeed, that's the right way of saying it. And that was a big problem for a long time for various subtle reasons, and Dirac wrote down that equation. And one of the things that his equation implied was the existence of antiparticles, which for a long time was like, okay, well, we'll believe it when we see it. I think at first maybe he even thought it was wrong because of, we don't see the positron. We don't see something which is like the electron that annihilates it. And then people found the positron, which was a tremendous prediction of Dirac's. It was confirmed. I think largely the reason that he won the Nobel Prize in physics, because of this prediction of the antiparticle of the electron.
He's
which
from the
was then
60s, 50s?
No, he was doing most of his work. I mean, he
50s,
lived
right?
until
Was that in the 50s or 60s?
the Dirac equation has to be from the 30s.
Oh, that far.
Yeah. But he lived until like 1990, I think. He lived to be a very, very old man. There's an amazing biography of him that I can't recommend highly enough. It's called The Strangest Man by Graham Farmelo. I'm not sure how to pronounce his name. It's one. I read it for the first time this past year, actually right after my daughter was born. So I was like laying on the couch with a sleeping baby on top of me reading this biography of Dirac.
And he was strange?
He was a weird guy. So now I think the consensus, as much as one can say these things, is that he had some kind of autism, but very, very highly functioning. But he was notorious for being just a totally awkward guy. Wasn't quite sure how to navigate the politics of Cambridge for a long time.
He was a vampire, Dracula.
Yeah, Dracula. That, I've never heard someone say Dracula before.
I like that.
Genius.
You can use that, Brian.
I love that.
All right, so we have L Dirac plus L mass.
Basically what that is that's the equation that governs all the electrons, quarks, and neutrinos in the Standard Model.
Okay.
And all of those are fermions. All of those have spin 1/2. All of those things. So that first line is literally just the thing that says, hey, these particles move.
Gotcha.
That's it. The next line.
Well, what about El Dorado?
We didn't get very far, Steve.
El Dorado. We haven't found El Dorado.
We're still on one. Huh?
That's right. A dream of theoretical physics is to find El Dorado.
Brian, we cannot possibly get through this whole thing.
No, I'm aware of that. But actually,
Without sidestep, I think we should try.
Only 10 hours show.
yeah, that's right. So the rest of it, here's the cool thing, is that pretty much, okay, so actually let's skip to equation 4, which then, so equation 2 is all the particles, right, the electrons, the quarks, the neutrino, etc. Equation 4 are the force-carrying particles, the gauge bosons.
Cool, okay.
So what we have there is that first thing G,
Yes.
G squared, is the gluon. That mediates the strong force, the force that ties the quarks together. So every term in this equation basically just says, hey, the force-carrying particles also move. The gauge bosons also move. It's the kinetic energy, essentially.
Can I ask you a question? Could you write this entire thing from memory? Do you live and breathe this so much that this is in your head?
This, I could derive it. I probably couldn't just write it down.
Yeah.
Yeah, pretty much.
That's cool.
awesome.
What I couldn't do is tell you the values of all the masses and interactions.
You don't
and
have that
everything.
memorized.
But yeah. But actually, just from knowing that the general form is relatively easy to write down from memory. If you ask me to remember all the parameters. So the Standard Model famously has 19 free parameters that things like, so I'll give you 9 of them right away. The masses of the 6 quarks and the electron, the muon, and the tau. Okay, so there's 9 basically free parameters that this doesn't specify. You just have to figure them out experimentally. Then there are other interaction terms, etc. The mass of the Higgs is another free parameter. This doesn't specify the mass of the Higgs.
Figure them out by doing colliding stuff?
Yeah, experiments. Okay. That's right.
So you can't derive them. You've got to observe them.
Yeah, exactly. So one of the reasons that people like string theorists exist is because we would love to say, hey, here is the dream of every theoretical physicist, which may not be ever achieved, I think is actually unlikely to be ever achieved, is the following thing. I hand you an equation. From that equation, you derive every single property of our universe. And let's even be a little bit modest, right? Let's just talk about the microscopic properties. So for example, the masses of all the fundamental particles. So actually, in the 80s, famously, string theory had just kind of come out and been realized. And string theorists, there was a famous quote, I think, by David Gross, who is now a Nobel Prize winner for not for string theory, for something else. Basically, he was like, "Okay, guys, mass of the electron, we've got it. Like, we're going to get this. We're going to derive it from first principles of string theory."
Okay.
All right, it's 30.
I remember reading about that.
Yeah.
Never happened.
It never happened, and it's never going to happen.
Yeah.
I'll give you another example of something you can't derive
Don't
from
tell
string
Sheldon
theory.
Cooper.
We can't derive the number of dimensions we live in. String theory is consistent in 10 dimensions, right? You would like to have some principle that says, okay, of those 10 dimensions, 6 of them curl up real small, and then 3 space and 1 time stays time.
Now, who the hell understands that? When you're talking about dimensions, you guys sit around, you're actually talking about dimensions.
Yeah, real dimensions.
Like,
That's right.
isn't it true that the human mind is not built to understand beyond, like, the 3
or
physical
4
dimensions and the
maybe
1
4.
temporal dimension? How can you talk about another dimension?
Mathematically.
Yeah, that's right. So saying the human mind is not built to understand, I think, does us a disservice, right? Because what it presupposes that we can't up the level of abstraction to something where we can make predictions and say things. So mathematicians all the time, not even physicists, but like mathematicians work in higher dimensions, 5, 6, whatever, how many dimensions, and you can write down the abstract formulation, and basically by doing the calculations, you get some intuition about how these things work.
All right,
so Jay, you're referring to imagining what's at right angles to reality. Yeah, we can't imagine that.
Right, that's what I was talking
you could
about.
talk about 100.
I can't visualize it.
You can't
You're saying
visualize it.
visualize. That's something
We're very
that I
visual
can't do.
creatures.
Yeah.
And is there still a discussion? So, when, from my understanding, like Einstein's real brilliance was in taking the sort of other people had come up with the idea that you have to like the Lorentz transformations, right?
That's right.
And
I mean, famously, those are a symmetry of electromagnetism, right? They're named after Lorentz, and I'll let you finish.
so the point is that Einstein's like, no, this isn't just some mathematical trick that we're using to make the equations work. The universe actually works this way. Time and distance are actually the variables. And so I always think of the same thing, like when we talk about this sort of stuff, like, mathematically, you are dealing with these higher dimensions. Is that just a mathematical construct, or is the universe actually built that way? Is that a conversation that we're still having over and over again in physics?
Sure.
Yeah.
So just to say something about the Einstein thing, because I think it's interesting.
Yeah.
One, I think really the leap Einstein made was to say, look, there's these Lorentz transformations, the symmetry of electromagnetism that was not seen in Newtonian mechanics.
Yeah.
And really Einstein's big leap was to say, hey, what if this was true for everything and not just electromagnetism, right? There's nothing special about electromagnetism. Maybe this is just the way the universe works, and now we know that's right. As string theorists talk about these extra dimensions, these are real spatial dimensions. The universe at some point, in the very, very early universe, it had 10 spatial dimensions, which things could just travel around in. The thing that has not worked out, and I think honestly probably never will, is that 6 of those are curled up spatial dimensions, which we no longer have access to, and then 3 of those spatial dimensions stay big and we can walk around.
Yeah.
But people take this idea seriously. So people do experiments, actually.
But Brian, is it to really, like, does the equation, is it possible for us to really get to these equations, the ones that are really going to explain everything?
It may. It depends. I think people, as this program has not panned out, and it's a very hard problem, right? So you don't want to give up on it because we've only been
Theory of Everything? Is that the movie?
That's it. Yeah. We were trying to remember the name of that movie before.
Oh yeah, the Hawking one.
So Brian, would you rather have $1 trillion or one of the unfound equations or uncreated?
$1 trillion? I think $1 trillion.
Yeah, I mean,
Are you kidding?
Well, you said it's what I'm trying to put a dollar value on it.
$50.
No, but you know what I mean? Like, how important are these equations? Like, what would one of these equations actually be worth if you had to put a dollar amount on it? That might sound crazy, but I know that's weird. But
That's a great question.
Let's make a deal.
Like, how much?
There actually could be a cost. So if you calculate the cost of the research it would take in order to accomplish the equation.
Yeah.
But it's not just the cost to
It's
create it, but what's it
it's
worth
more
to
than, It's more than $1 trillion.
More than $1 trillion, right? More than $1 trillion.
Okay.
Because if you wanted
That's
to
a
test,
bargain, actually.
if you wanted to test something like string theory, right? I mean, it's You have
beyond
to
our
build such a crazy big accelerator. I'm sure, if we just extrapolated the size of the LHC cost per whatever meter circumference or something, we could probably come up with a number, and I'm sure it's bigger than $1 trillion.
Yes.
Hold on, Steve. Hold on. All right. Alien spaceship lands.
That's where I was going.
Stop. I won.
Okay.
I won.
Yeah.
Alien comes out. Brian, I can speak English.
So this alien knows, the alien knows who I am is the relevant thing here.
I can speak English.
Keep going, keep going. Okay,
use your hands too.
I'm
use
listening.
your heads too.
I will either give you this equation or $2 trillion. Choose wisely.
$2 trillion.
Two extra.
There you go.
Why does he have done? No, you give 2,000 Quatloos.
I'll take the Quatlo. The exchange rate on Quatlo.
Turns out they're just Star Wars candy.
Look what it did for Kurt.
No, but
Not Bitcoin.
Would the sudden appearance of one of these super advanced, awesome equations do anything to humanity? Or would it be better to just say, I've got $2 trillion to do awesome things for the
Well, one
world?
thing I think
Brian
it
could
would.
finally publish.
Yeah, that's right. Fine, have my first paper. One thing it would do is I think it actually would be an amazing. It would be sort of like if we knew for a fact that there was a that there really was a single correct unified theory that described everything.
Yeah.
That would be incredible. I mean, that would be
The achievement of humankind.
That would be that's the point of theoretical physics, of theoretical particle physics. Really, is precisely that equation. So that would basically be saying, the goal has been achieved. Like now we've got it all.
But what can we do with it? Can we build cool stuff? Can we
Dyson
allow
spheres?
us to do like
Wi-Fi
Not really. Again, for the same problem is that we don't the things that we see and deal with every day, even on an atomic scale, much less a macroscopic scale. This stuff, doesn't really matter so much for.
Okay.
Right? Once you get bigger and bigger and bigger, it's not going to solve any engineering problems.
Or like for time
like
travel,
nothing like
or
that.
for
So
like
fusion is a nuclear thing. This is below nuclear scale.
Jay, you could
Like
you could
the string
replicate-
theory is below a nuclear scale.
Something may come out of it that we can't even anticipate, though.
Yeah, that's entirely
wormholes.
true.
You can't.
But the thing is, Jay, your reality, everything that matters to you, is really just a subset of the particles we're talking about.
No,
here.
I
You
get
really
that.
don't need
No,
a lot more.
I totally get it. I'm just, when I think about the practicality, it's like, okay, and I'm not saying that this isn't important because I still think it's important. I still think that God, there are people that get this like you, but
there's got to be a payoff.
yeah, like I always thought
in the
though.
Western model, like something valuable.
Let's ask the more basic.
Visibility.
Let's ask about something that already happened, right? The Higgs. We know the mass of the
Yeah.
Higgs. What's that doing for us? Nothing.
Okay.
Right. It fills in the blanks in the standard model. It helps nail down
There's
these
no
things.
immediate practical
Engineering-
Wait, no, I
That's
disagree.
right.
It's great podcast fodder. We've talked about that a million times. What would we do without it?
But there's no engineering thing that's doing for us, and
there
I mean,
won't
maybe
be?
there will be someday. But
Okay.
these are all very unstable.
But just understanding is cool
It's
enough.
discovery.
And then maybe
No,
there will be
it's
someday.
discovery.
I would liken it to, actually, it's not unlike the alien life thing. It would be knowing our place in the universe of
Exactly.
science. There exists a unified approach, and that is not an obvious statement. And in fact, what I was about to say before is, as this program has not reached a successful conclusion where, string theory, obviously it works and it gives us everything we want, more and more people are defecting from this kind of reductionist approach and saying, okay, maybe we're actually wrong to keep doing, looking at the universe at smaller and smaller scales because there's no unified formulation. And that is a intellectually totally coherent approach to physics. It could be the universe we live in could just be a bunch of initial conditions. This is what the mass of the Higgs was. This is the cosmological constant. This is the mass.
There
of the
may not be
electron.
one equation.
Yeah, it could be just a bunch of random points.
And we learned something about our intellectual approach to answering questions,
Totally.
which itself is extremely valuable.
But wait, if we met aliens though, like how they say pi would be like something that we could actually
Talk about.
there are things that aliens that are intelligent that would come up with answers. Like they may very well have their version of these equations that
I mean, these are. Well, there's another interesting question there, right? Do the laws of physics look the same everywhere in the universe? As far as we know, they do.
Yeah.
But one could imagine if they come from a causally disconnected patch, by which I mean,
How
some
would they
other.
get here? How would they get here?
Well, if they've invented warp travel or something like that.
true.
So let's say they come up from some part of the, if you like, multiverse or universe that we can't interact with, right? Their laws of physics could be totally different.
Like
than ours.
interdimensional kind of
Yeah, kind of. You could sort of think about it that way.
But even if their laws are the same, they just may be looking at it sideways to us.
Right.
You know, they just may be looking at it in a way that it's still, it kind of all is the same, but they're just thinking about it in just like a way that's bizarre to us. But it works.
One example I like of that is I forget. I wish I could remember who said this first. Might have been Wigner, but I can't remember. Anyway, the thought experience was: let's imagine a sentient species, that has our rough level of thinking, but who grew up in the ocean and in water, right? Maybe to them, what we consider a very hard thing, which is hydrodynamics, fluids, turbulence. Right? Turbulence is really hard. Maybe to them, turbulence, they've developed the mathematical machinery that turbulence is very easy, but these kind of Newtonian point particle things that we deal with every day, maybe that to them is the hard stuff.
Yeah.
And so it's possible they just have a different kind of mathematical outlook because of their, to us, balls, rolling down ramps and stuff like that. This kind of Newtonian bread and butter physics is how we think about the world. Right. Maybe it looks different to them.
By the way, the point I was going to bring up before is every time somebody claims to have spoken to aliens and to have received some kind of important message, it never's the next equation.
I know, gosh, right.
It's never anything that would really represent any kind of scientific or intellectual breakthrough. It's always the most
peaceful and love and love
don't
your
blow yourselves up
neighbor.
with a nuclear war. Thanks for that.
It's always.
But Steve, even in science fiction movies and TV series, the characters encounter aliens all the time, new technology all the time. No one says, "Hey, give me the ultimate equation." Come on, nobody even mentions that because it doesn't support the plot, obviously. But I mean, that's what would be one of my first things.
Did you guys ever see that movie Real Men with Jim Belushi and John Ritter from the 80s? Right, there was a choice.
Wow.
This alien. It was on HBO all the time when I was growing up.
Right.
It's actually pretty funny, but at the end they have to make a choice from the aliens: do you want the good package or the big gun? And this is the bad guys are trying to get the big gun, which can blow up the entire Earth.
Yeah.
And they live on Earth, so it's not a great idea.
Yeah.
And the good guys, Jim Belushi and John Ritter, are trying to get the good package.
What's the good package?
I think
they want a good package, or
the good package. It's something like it'll feed the whole world.
Yeah.
Oh, that kind of package.
If it's as good as I remember it being 30 years ago.
Okay, yeah.
One time I was at a channeling once when I was trying to do this TV pilot thing, and at the end of the channeling, the guy was talking about how he was communicating with aliens, and they want peace, they want love, not the next equation, but they want to communicate. They're communicating to him so that he can then have these classes, in a loft in Brooklyn for 10 people at a time to communicate the message of peace and love from the Pleiades or whatever. And I said, okay, do you think that's the most efficient way to do it? And he kind of looked at me, and for 1 second, there was 1 second, I was like, yeah, probably not.
Yeah.
And he said, no, but they're about love.
That will ruin my financial.
Almost
there.
Yeah.
So am I right? Both of you guys have to leave in 10 minutes?
Is it almost 3 o'clock?
Yeah.
Yeah, I got to
All right,
leave.
if that's the case,
Yeah.
maybe we do another if.
Okay, one quickie.
He's going to ask very profound questions.
Right.
To answer.
If you could give a single piece of advice to the film industry in Hollywood, what would you say?
Hire Phil Hudson.
Absolutely. Plot matters.
Yeah, plot matters.
Plot matters.
Yeah. How about this?
Please do good
take
stories.
Take 3/4 of your money that you were going to spend on special effects, and spend it on better plot and better dialogue.
Well, I don't mind the over-the-top special effects as long as it's supporting. It's not gratuitous, and it's supporting a plot that actually I care about, characters I care about. There's no substitute for a good film.
Okay.
That's the problem. Hey, we were going to talk about Eyes Wide Shut.
I wanted to talk about that. I know. I wanted to talk about that too.
Dude, take the next 10 minutes.
So we got 10 minutes.
Real quick, my advice: give Joss Whedon anything he wants to do whatever way he wants. That's my advice.
They are, Bob.
I would say spread out the funding, right? Take more chances.
Take more chances.
Oh, seriously, yeah.
That's the big one.
$10 million
consolidated.
Than $100 million
That's
film,
right.
or
With
one $400 million
That's right.
film.
With digital, really take some total unknown. Give that person, $100,000, which to a studio is no big deal. To that person is an infinite amount of money. See what they can do with it.
Give some independent person $5 million and say, make a Batman movie.
Mm-hmm. Yeah.
Make an awesome independent, give them the rights. Make a cool, or make a Star Trek film where it's like a character study. It's like two people just talking.
And hire science advisors.
Yeah.
Yes.
Yeah.
Please.
How about this? Let the writers
writers
write, and don't let the executives destroy what they wrote. Because that's what happens.
All right, What's your problem with Eyes Wide Shut?
Yeah,
So
what's
this
okay,
is
now,
Kubrick-
bearing in mind,
Kubrick's last film.
I saw this 15 years ago and hated
Yeah.
it. So this is not
Bio break.
I might watch it now and totally love it. To me, it's pace. And I don't mind slow movie. Have you guys seen Paris, Texas? It's a great
I know of
narrating
it.
stand. Is it Wim Wenders? Is it Wim Wenders? Who did Paris,
I don't
Texas?
think it's Wim Wenders, but
Okay,
yeah.
I can't remember. Anyway,
yeah.
I have no problem in general with slow movies. To me, the pacing of that movie was so glacial, and the way I'm assuming the way he directed the actors was to
Every
to accept
every
that,
line
the,
of dialogue.
that just
Takes
almost
us-
viscerally
Yeah.
drove me insane.
Yeah.
That's my big
So-
problem with it. So
And it also seems like someone's idea of what New York, people living in New York, could be like. Like there seems no connection to what, and there literally wasn't because it was a set in London. But it's like this
Right.
sort of pseudo-idealized version with this glacial pacing. I didn't find any. The characters I didn't connect with at all.
Yeah.
I didn't find
Yeah.
their
I could see that being
motivation.
because it's a movie about essentially the tension of a marriage, right?
Yeah,
I
which
could
is-
understand that being actually I can understand all this being a completely conscious choice.
Yeah.
But for me, the unreality didn't bother me as much. The pace, I just couldn't do it, and I didn't see. I guess the other thing is I didn't see the justification for how slow it was.
And then ultimately, on top of everything, is the fact that he wanted to make this erotic adult thing, and he chickened out by hiding the sequences with those.
Although,
clothes.
actually, speaking of the studio system, maybe that was probably.
I'm sure it was,
or
but it's
whatever,
Kubrick.
but yeah,
I mean,
right.
then he should
could have
just
done-
say, "I'm not going to release it with a
So,
with a rating or something."
can you? I'm curious. I mean,
That
can
to
you
me was the
defend all
most-
these
So,
choices?
first of
In
all,
6 minutes.
every choice was absolutely deliberate.
It's
Yeah.
Kubrick, so I
It's
imagine
Kubrick.
it
So
was.
you just have to.
Have you guys seen Room 237?
Yes.
Yeah.
Yeah,
Yes.
right.
But
Yeah.
that's sort of
a-
pattern recognition.
Right,
That's
exactly.
different.
No, I understand that.
Yeah.
But the point is, you shouldn't underestimate Kubrick.
The thing is, it's hard when you're saying the movie's about this or about that. The thing is, it isn't really about those things. You know, there's no connection to reality. Kubrick is trying to create something, and from my reading of the movie, I think what he was trying to convey was. A lot of what Kubrick did was inspired by Civilization and its discontents. A lot of ideas are in there, like so the movie was trying to portray like a microcosm of civilization, and like what is civilization? Why did we create the civilization? What are we trying to do for it? For example, there's lots of scenes where there's just like an excess of stuff, right? So like the rich guy who is in his home, there's a table just full of booze. Remember that?
Right,
just
right.
gratuitously large amount of food, which is very similar to the scene in The Shining, where they have a long scene where he's
right.
describing how much
All the
food
food in
is
the
stored up.
pantry,
It's like that's all the hotel. Also,
the Scatman Brothers is.
The Overlook Hotel is also sort of just this is civilization.
Right.
This is so one of the things that happens in civilization is that we try to ensure for ourselves sex, power, food, all the things we think we need, and that's again the rich guys. How the part of that was the people with power securing things like sex, but. And the plebes can't have access to their women,
Right.
Which is why
No
they were
way.
so upset about that. But what I read is like the main character, Tom Cruise, his whole journey, he was seeking the thing that people seek. He was looking for sex the whole movie. That was basically his whole motivation.
yeah.
Everything he was doing was just. It wasn't really about his marriage. It wasn't about New York. It wasn't about any of that. It was about a guy looking for sex. And throughout the movie, there is this continuous connection being made between sex and death. Did you get that? There's this constant
Not that I remember,
confusion,
no.
constant confusion about is she dead or did she get laid?
Oh, yeah, with the cadaver,
And
yeah.
there was also definitely, and I'm not even really sure what Kubrick's ultimate point is about sex and death, other than there's no question he was associating the two. Think about every scene in that movie where there's a sexual tension combined with some like the funeral, like he goes to his patient who died, and like the woman hits on him, and there's like the dead bodies right there, and then he's like almost having a sexual moment with the corpse of the girl that he was seeking at the end, and then when he's confronting the guy, he's like, she's not dead, she's at home getting banged by Mr. whatever, It's all that confusion. Is she dead or is it?
But explain the pace.
So I think it's supposed to be cold, frustrating,
Uncomfortable.
uncomfortable. You are supposed to experience what he's experiencing watching the movie, which is
That's fair enough. which is exactly
you could feel how
Yeah.
frustrated
Totally,
he was
totally.
throughout the whole movie because you were frustrated, and then he couldn't even get laid with a hooker because she had AIDS. Right. Again, death kept getting in the way every time.
Did you
until the very end of the movie when finally what's the last word of the movie? What's the one thing we haven't done? His wife says this. What's the one thing we haven't done? Fuck.
Oh, fuck. Okay.
Right, that was the last line of the movie. So anyway, it's hard to summarize that movie in 3 minutes, but think about it
I should
just on a lot deeper level. Yeah, and Kubrick actually was very good about having like a superficially enjoyable movie with the deeper stuff too. I do think in Eyes Wide Shut, you had to it was harder to appreciate on the superficial level. I will grant you that. I will grant you that.
I'm curious, did you see it in a theater or did you see it? Okay, so I saw it, this is when I was in grad school, on a terrible television that was probably,
I could see how that would be a different experience.
And probably was a very different experience.
I find his filmmaking so gripping. The pace didn't bother me, to be honest with you. I was just,
you have
and of course, you get immersed in the feeling that he's creating and why he's creating it and everything.
So like the pace of...
Pace of 2001 was also...
Yep, I mean, 2001.